Hello folks, it's Mr. Ray here with beginning our next unit, which will be on trigonometry in advanced functions course. Um, so this will cover a variety of topics. A lot of the stuff you're going to need to know what you learned in grade 10 and 11. We'll do quick reviews of some of the concepts when we get there. The first lesson in this unit is called radian measure. So we're going to talk about a new unit that we can measure angles in, and in fact, this new unit, radians, is going to be basically our go-to standard. We'll be using radians instead of degrees. Now, I know everybody thinks in terms of degrees. You've been brought up with it all your lives in math, and that's understandable. But think of radians, angle measurement. Think of angle measurement as sort of like temperature. Okay, there's two main units for measuring temperature. One of them is Celsius, which we use in Canada and most other countries in the world. And then there's also Fahrenheit, which is used in, I believe, 2 countries in the world. So you may understand both quite well because you may hear broadcasts from the US. They use Fahrenheit pretty exclusively. So for Canadians, we're pretty used to using both. We can understand that, 28 degrees is nice weather. You can go out and suntan, and it's equivalent to approximately, I don't know, 75 degrees, 78 degrees, something like that. It's the same thing with angles. So it's the same angle we're measuring, we just use different units. Okay, so I'll be talking about where this radian measure comes from. We'll also be looking at another concept, a couple of concepts. One is called arc length, and the other one will be angular velocity, which will be our last example. Okay, so the first thing to talk about is, well, what's a radian? Okay, so I'm going to use this picture down here. It's not really supposed to be for a radian, but that's what we're going to use it for. So we've got a circle with a center at C. We've got two radii that go from the center of the circle to the outside of the circle, and it creates what we call a sector, and it uses, there'll be some angle measurement here. It's almost like a piece of pie, like what's the angle of the piece of pie, and outside here we have the arc length. Okay, now what's a radian? Well, a radian is when we take the radius to radii. If we go exactly 1 radian along the arc, okay, so it's sort of like a equilateral triangle, but not quite, because this arc is not straight, obviously, but it's similar to. Then this measurement, this angle that's in here, is 1 radian. Now I know this is kind of confusing. That says radian there and there. This is really the radius. This is the radius, and this would be 1 radian. Okay. Yeah, so we'll be talking about how to convert back and forth between degrees and radians. It's a pretty simple formula, and some of them you'll just get to know over time. Pretty standard angles like 90 degrees and 180 degrees. You'll know exactly what those are in radians by 3 or 4 lessons in for sure. Now, a couple of the terms here. Central angle, that's the angle that's formed by this 2 radii. Okay, and we still use the symbol theta as our go-to variable for angles. That hasn't changed. The arc, like I've talked about, is basically it's the piece of the circumference that's made from these 2 radii, and the verb subtends. Okay. You see that as a definition of what the arc length is sometimes, actually down here. So subtends means across from. Okay, so when I read this key concept here, the radian measure of angle theta is defined as the length A of the arc that subtends the angle divided by the radius of the circle. So this is actually a formula here that we're going to use to actually calculate the arc length. But the verb subtends, we talk about this arc subtends from the angle. Okay. This will be the only lesson you'll ever hear that word. So as long as you understand the relationship between the arc, the angle, and the verb subtends, you'll be fine. Okay. Now, if I just do a little aside here. So if I was to, okay, let me do this circle up here. So there's our circle. If we do our kind of unit circle initial arm here at the positive x-axis, if I create an angle of 1 radian, so that's kind of like this, where it's almost like a equilateral triangle. So these two sides are equal. Obviously, it's the radius, but this is also the radius. If I was to measure that with a piece of string, not point to point, so that would be 1 radian. If I add another one here, exactly the same. That's the same as that. That's 2 radian. So that angle measurement would be 2 radians. And one more over here. Now this is obviously not perfect, but that would be the third one. So that measure from there to there would be 3 radians. Now, if I was to draw a straight line to basically make this into a semicircle, what we find out is that this is 0.14159 radians. So we've got 1 radian, 2 radians, 3. So a total of 3.14159 radians, and that number that we just said, 3.14159, ... that's pi. So basically, from that, we know that 180 degrees is equal to pi radians. And instead of writing radians every time, we'll tend to use the abbreviation for rad. Sounds better anyways. So 180 degrees equals pi radians. And that's kind of where the number pi comes from. Okay, it's related to circles, obviously, and that's where it's brought out with the radians. Okay, let's go down here. So we've got this formula here that allows us to calculate, if we know 2 of these 3 things, the angle, which is in here, the arc or the radius. If we know 2 of those things, we can calculate the third thing. We'll have an example that does that. Here's our comparison here. So I just told you about this. Pi radians equals 180 degrees. If I was to go all the way around the circle, instead of a semicircle, it's a whole circle, return, that's 360 degrees. That would be equal to 2 pi radians. Okay, so these are actually, if we just multiplied both of these sides by 2, we'd get that. Okay, now, because pi radians equals 180 degrees, there's a very simple conversion formula, because we would, well, I can put the units here as well. Pi radians, which is equal to 180 degrees. So this actually, they cancel each other out because it's the same angle. So I can multiply by pi over 180 degrees, or 180 degrees over pi, because that's also equal to 1. So if I want to convert, if I have degrees and I want to convert to radians, I use this version. And the best way to think about it, if you're not sure, if I want to change degrees to radians, it means I want to cancel out the degrees. Okay, so that means my degrees should be on the bottom of the ratio, because say I had 60 degrees times this, well, the degrees for 60 would cancel with the degrees from 180, and then you're just left with the units of radians. Okay, and then vice versa, if we started with radians and we want to convert to degrees, we just flip that ratio upside down. And again, if we start with radians and we want to create degrees, well, we want the degrees to be on the top so that we actually have degrees in our new measurement. Okay, so hopefully that makes sense. Here's our first conversion. We want an exact and an approximate radian measured to the nearest hundredth for an angle of 30 degrees. So we'll actually calculate the exact value and then just show what it would be in a decimal format. So start off with our 30 degrees, and now we're going to multiply by one of these two ratios, which is equal to 1. So in this case, we want to have the degrees on the bottom, so that would be pi over 180 degrees. Okay, now you can see well, the 30 will multiply on the top, so I'm going to have 30 pi over 180, and you notice I don't have any degrees anymore because those canceled each other out. And you can see that I have 30 and 180. Well, I can divide top and bottom by 30, and I get pi over 6, and that's in radians. This time I'll actually spell it out, and this is the exact measurement. Okay, I didn't do any rounding. Okay, so, and this will be an important measurement when we look at our unit circle in the next lesson. 30 degree multiples of 30 degrees were very important in the unit circle. So pi over 6. Now, for some reason, mathematicians like to say pi by 6, like sort of like pi divided by 6, but without the divided word. So that's pi by 6 radians. Okay, that's the exact. Now, if I want to find the approximate, I just go in the calculator and press the pi button. Don't just type in 3.14, use the pi button every time. So pi button divided by 6, and that gives us 0.52 radians. The time I'll use the short version. Of course, this is approximate. Okay. One other little thing here. If I want to know how many degrees is there in 1 radian, well, let's do a little calculation using the formula. 1 radian is equal to, well, it'd be 1 times, and in this case I want to use this ratio, so it's basically just the ratio, 180 degrees divided by pi, and that's equal to 57.3 if I round it. Okay, and that actually makes sense. If you go back to the analogy up here where, you know, 1 radian, it's kind of like an equilateral triangle. Equilateral triangle, that would be a 60-degree angle, but you can tell that this angle is going to be pinched a bit because this kind of bulges out, so the actual measurement will be a little smaller than 60. So 57.3, which we calculated, seems to make sense in that context. Okay, so let's go to the next page. A couple more conversion questions. So first, this time we're going to start with radians, and we're going to convert to degrees. So again, I'm going to start with my pi by 4 radians, and that's equal to pi by 4 times. Now this time I'll use the 180 degrees over pi as the ratio, and you can see quite nicely the pi's actually cancel out. And there's units there too, but we didn't write it. Pi radians cancel each other, and then we're left with 180 degrees divided by 4, and that works very nicely to 45 degrees. So that's exact. It's not, we don't have to round at all. Okay, and this one here, this is not, you see it doesn't have any pi values, it's just 5.86 radians. Okay, so just going to sneak back to the previous page, okay, just to give you an idea. Okay, so we know that half of a circle, 180 degrees is pi radians. If you think of the number pi, that's like 3.14. So I could write that as 3.14 radians, maybe a couple more decimal places to be more exact. But if I went all the way around twice, 2 pi, that would be 2 times pi, which is about 6.28. So one complete revolution is 6.28. So when I'm looking at this value here, 5.86 radians, that's probably going to be in this territory down here. Okay, it hasn't gone completely around once, but it's getting close. So you can kind of use that as a, just a sanity check of our answer, see if it makes sense. So 5.86 radians, that's equal to 5.86 times, and this time we use the reciprocal ratio because we're, no, actually we don't, we use the same ratio, 180 degrees over pi. Now you can't cancel anything here, really, because the pi can't cancel there, and these actually multiply. So you just go on your calculator, 5.86 times 180, and then divide the whole thing by pi, and we get approximately, so we have to round this time to the nearest tenth, it's 335.8 degrees, which makes sense because we figured it was down in that fourth quadrant, getting pretty close to 360. Okay, so hopefully that you can convert any angle from degrees to radians or vice versa using this very simple conversion ratio, 180 degrees over pi, or pi over 180 degrees. Okay, the next question. This is going to be using our arc length calculation. So this has to do with a carousel ride, and Suzette's riding the camel. Camel is 9 meters from the center of the circle of the carousel, and if the carousel turns through an angle of 5 pi by 6, obviously that's radians, determine the length of the arc excuse me, traveled by the camel to the nearest tenth of a meter. Okay, so should probably start off with a picture the first time we do something like this, and that's not the nicest circle, but it will do. So we basically know that the radius of the carousel or the circle is 9 meters. Okay, and we know that basically the camel started here and it turned. It doesn't really matter which way it turned, but it went around 5 pi by 6. So 5 pi by 6, if you think about it, it's not quite pi by 6 because it's like 5/6 of pi, so it's probably going to be around here. So I'll just draw something close. So this is also 9 meters, right? It's just another radius. This angle here is 5 pi by 6. And what we want to find out is what's the overall length of this arc. So A equals what? Okay, so let's list off our values because we know, I'll write the formula over here. We have a theta, which is the angle, equals A over R. A is the arc, R is the radius. So we know that R is 9 meters, and we know that theta is 5 pi by 6. Okay. Now, if we want the arc length A, I'm gonna have to rearrange this formula a little bit. So multiply both sides by R, and I get A is equal to R theta. Okay. Like I said at the beginning, you can use this formula if you know 2 of these 3 things to get the third thing. So they could give you arc length and radius and calculate the angle, or they could give you arc length and angle, calculate the radius. So if we plug in our values, we get A is equal to R, which is 9 meters, times 5 pi by 6. Okay, and I plug into the calculator, I get 23.6, and the units are going to be meters because the radius was measured in meters, and that's what we're looking for the answer. Now, one really important thing here, you can only use this formula if your angle is measured in radians. So this must be in radians. Which makes sense because you're multiplying by an angle, which you've probably never done that before. So it makes a big difference whether it's 5 pi by 6 or, whatever 5 pi by 6 is, like 160 degrees compared to, less than pi. You're gonna get a totally different answer here. So you can only use this formula for arc length if your angle's measured in radians. Now, could give you a question where I give it in degrees, but you're gonna have to convert it to radians before you can use the formula. Okay, last example. This has to do with the angular velocity. So you'll see a couple of these questions. It's just a matter of kind of figuring out the steps you have to do. So, let's just read this. The angular velocity of a rotating object, so this is the definition of angular velocity, is the rate at which the central angle changes with respect to time. The hard disk in a personal computer rotates at 7,200 RPM, rotations per minute, revolution, same thing. Determine its angular velocity first in degrees per second and radians per second. So instead of measuring the rotational speed and how many rotations per minute, we want to know how many degrees per second this hard disk is turning. Okay, so the first thing we have to do, because this is measured in minutes, rotations per minute, this is per second. So I'm going to have to do this for both. I'm going to convert into seconds. So it'll still be rotations, but we want rotations per second. Okay, so we've got 7,200. This stands for, I always say rotations, rotations per minute. So that can be written as 7,200 rotations or revolutions divided by 1 minute. So rotations in 1 minute or per minute. Okay, but we want this in seconds. So this is a good science technique where you're converting lots of units. In this case, we're really only converting one. So it's kind of like what we just did with converting degrees and radians back and forth. So we're going to multiply by this ratio, which is always going to be equal to 1. So 1 minute, I'm going to put 1 minute on the top because I want it to cancel with that. And 1 minute is the same as 60 seconds. So I'm really not, when I multiply by this, it's kind of like when I multiply by pi radians over 180 degrees, it's equal to the same thing. So we're just going to get the units changed here. So you can see very nicely the 1 minutes cancel out. We're left with 7,200 rotations in 60 seconds, which is, see, it's the same number, it's just different unit on the bottom. But the good thing now is we can actually get it per second. We divide that out, cancel the zeros. 720 divided by 6 is 120. So 120, is that 120? Yeah. So 120 rotations per second. Okay, so we haven't actually answered the question yet. We've just changed the platter speed into a per second. How many rotations in 1 second? The rest of it's not that bad. So the angular velocity, a lot of time, most of the work is changing the units to what you want, and then the actual calculation is kind of, a lot of times it's less work. Okay, so what we do now, since the first one we want in degrees, so at the top I'm going to put, one rotation is the same as 360 degrees, and we have 120 rotations per second. I'm not bothering with the units here. I'm just going to put it in the final answer. That works out to 0.3. Sorry, not 0.3, 3.0. 3.0 degrees per second. And that makes sense because if it went around a whole 360 degrees, you'd need to multiply that by 120. So it'd be 360 seconds it would take. Sorry, 120 seconds. I'm getting myself mixed up. But it's 3.0 degrees per second. That's the angular velocity. So every second, the rotation is changing 3 degrees. It's adding 3 degrees as it goes around. So in 120 seconds, hold on, that doesn't make sense. Let me just pause this. Okay, it turns out I was just second guessing myself. That is correct. So the angular velocity is 3 degrees per second, and we want to do the second part, which we're just changing the units. We want radians per second. So really, we don't have to recalculate the rotational speed in seconds. That's already done. So we're still going to use the 120 here. So now we're going to do, again, angular velocity. But this time, instead of using 360 degrees, we're going to put 2 pi at the top. And that's going to be over 120 rotations per second. And we divide that out. We cancel the 2, get a 60 on the bottom, so it's pi over 60 radians per second. Okay, so that's it for basically just remember, how to do this formula once. Make sure you're working with the right units. That's usually the biggest mistake being made, is not creating the right units that you need for the question. Okay, and then whether you're using degrees per second or radians per second, most of the questions I think are going to be radians because, like I said, we're basically converting into that, but it's just changing between the 360 degrees and the 2 pi radians in your calculation. So got some homework questions for you to try out. I believe the next lesson we're going to be looking at the unit circle, and if you remember when we created that grade 11, we used the special angles, multiples of 30 and 45 all the way around the circle, and we're able to come up with the coordinates around the unit circle that helped us figure out the values of sine and pi and tan for those angles. The only thing we're changing will be to, instead of using degrees, 30, 60, 30, 45, 60, 90, etc., we'll be converting those into radians. So that should be pretty straightforward, okay? All right, so that's it for today. I'll see you in the next lesson.